Hi, my name is Zach Johnston. I'm doing my presentation on 2212 processing, which is a superconductor that's second only to a YIPCO, basically. And this is what I did my undergraduate research on. Today we'll be talking about the 2212, its background, how it's good, some of the problems that we're having with processing it, what my research particularly was, and what I'd like to do in the future if it works. To begin with, 2212 stands for bismuth, strontium, calcium, cupric oxide, and again it is the second best high temperature superconductor. But we can't use it in magnets just yet because of the processing issues. It is sheathed in pure silver, and they use the powder and tube method. And they do this several times to get a great many number of individual filaments. So the powder and tube method is where you take 2212, you break it up into little bitty pieces, you insert it into a silver tube, and you extrude it until it's a much thinner tube, close to a wire. You restack it and do the same thing again and again and again. And so this gets on the order of several hundred filaments. And so this is an image of a 7 by 85. So there'll be 7 large tubes that had 85 individual filaments in each. And so that's around 600 each. 2212 is also a wind and react superconductor. So you have to make it and then heat process it, because if you try to deform it in any way after it's been processed, it will shatter because it is very brittle. It has a lot of advantages. So to begin with, the field, the critical field that it can go to is very high. This is Dr. Lee's graph showing all of the major superconductors in there. The field that they can go to along the X and their effective carrying capacity. 2212, along with YIPCO, we've yet to find, as far as I know, the maximum field that they can still be superconducting at. And to me, it looks like the 2212 is going to win out over the YIPCO just from the angle, but it may not. One of the advantages that it has over YIPCO, and the main advantage why there's still research going on, is that 2212 it does not depend on the direction. So the amount of current that you can put through does not depend on field direction. That is to say that right here, the YIPCO, if the field is parallel to the tape plane, so the YIPCO comes in as a flat tape. If the field is in the same direction as the tape, it's pretty good. But if it becomes perpendicular, like along the end of a solenoid type magnet, then it starts to go down, and that's what this is over here. And my current work, I actually have a full-time job over here at the Mag Lab working on the 32T, which is the goal is to make a 32 Tesla all superconducting magnet, and the inside 2 coils are both going to be YIPCO. And we're having a bit of an issue with this problem right here, because as the field goes out, it's not straight throughout the entire through the core of the entire magnet. As it goes up, it begins to loop back around like a solenoid does. And so towards the end, you have some misalignment, and you start to go from 2,000 amps per millimeter down to maybe 100, or yeah. So the silver that is put in is also an advantage because it's a bit of a quench protection. So if you take it above its field, if it has a jolt of force, then several other things can make it stop being superconducting in a spot, and then you need that current to go somewhere, otherwise it's going to burn up pretty quickly. It's also commercially available in pretty long lengths. We're having a problem with that with the YIPCO itself. We can't get it over 100 meters just because of the way that they process it. But the 2212 can be made pretty much that long. Another advantage is that the bismuth, strontium, calcium, and copper, and as well as oxygen, are all not rare earth metals. They're readily available and they're not that expensive, though the silver itself is pretty expensive. Some of the issues that it has. It takes 4 days or so to process 2212. So once you wind it, you then have to go through this long heat treatment schedule that is irritating, to say the least. Silver is also about 60 to 70% of the weight percentage of this. And as you know, silver is very expensive, on the order of $30 an ounce. The critical current they can carry, again, is not quite as high as the yttrium-based superconductor or the rare earth-based superconductor, which is why they're expensive themselves. And as I said before, it's brittle. Now, the main problem that I attacked was its internal bubble production. So when you heat treat it, it had a tendency to burst. You get it in, there'll be powder, and what powder is individual little crystals, and between the crystals has to be some sort of gas. Well, we wanted it to be pure oxygen, and that's what they asked Oxford to make it in. So they grind it up in an atmosphere of pure oxygen, and that's what it's supposed to be, so that when you process it, the oxygen can diffuse to the silver. But what was happening was something else that we were unaware of why. And so I came in and did my research on what the gases were inside of the bubbles. I did the research on what the content of the bubbles were. I used a mass spectrometer. We put it in a flowing oxygen atmosphere because we wanted the oxygen to be pure, and that's how you process it in the real system. So this would most closely represent what was inside of the wire. We heated it all the way to melt, which is well past what they actually processed it to, so that not only did I get melt of the internal 2-2-1-2, but the silver itself liquidated and I had big spikes, because then all the gas came out at once as opposed to little bursts here and there and some coming out of the ends. I measured the spikes, and then my final result was that there was a hydrogen and carbon inside, which came out as CO2 and H2 because we had, or H2O, because we had a flowing oxygen atmosphere. I used a Pfeiffer mass spectrometer, and the way this mass spectrometer works is you take in a very little bit of gas on this side, you snatch an electron off of the gas, and then accelerate it in one direction. That lack of an electron gives it a charge. You put a magnet next to it, and it's pulled down. And you have sensors along the wall, which tell you, depending on how far down it goes, what the mass is. And you get readouts, and you then break down the data. This is the system that I designed and built. It's a flowing O2 system. So here we have the heater that brought the 2-2-1-2 powder to melt. We had oxygen coming in, going through, and coming out. This is where the gas is extracted. There's a very, very, very thin filament in here that's made quartz that goes all the way into the chamber, the very, very low vacuum chamber, just like we had in Dr. May's lab tour. We filtered the O2 coming through so that we could see water spikes a little bit better. And the sample is held in here. This is a close-up of what the sample looks like afterwards. So we had a very small chamber. This is not as big as the tip of your pinky. And I tried to get it, but this right here is the best image of the filament that I could get. There's a very, very, very small quartz filament that's very easy to shatter. Okay. And again, the result was that the interior contained CO2 and water. So my future research is to help improve 2-2-1-2. As an aside, I didn't put it in here, they've done additional research over this past summer on high pressure processing of the 2-2-1-2 so that it doesn't matter that the bubbles are in there because it's under 10, 20, or 100 atmospheres, the 20 seems to be the best, of external, what's the name for it, hydrostatic pressure. So it's pressure from all around on the wire so that the bubbles don't get a chance to expand. And they've gotten much, much better results. They've increased it by at least a factor of 2 or 3. So my future research, my last research is kind of moot because now the bubbles aren't an issue. But they can still improve the critical current because what's happening is they're not processing the end is you're left with some 2212, like in here, this is a quench section. So they had it at the maximum temperature and then dropped it into oil or water or whatever. And then it shows you what's going on at that one time. So this is liquid that's going to turn into the 2212 phases, single phase, over the next day or so. And this is what's called the alkaline earth cuprates, which is 2212 without without the oxygen at the very least. This is the copper-free phases, so these are the chunks of material that don't have any of the copper in them. And neither of those phases are superconducting. What's happening is you're getting some of the material from these is being anodized out, or anodized out, what's the word there? And going through the liquid to the 2212 phases. So my idea is to use high frequency sound waves or pressure waves to try to help break those up into small crystal phases. And then that should also help reduce the long time to get it to liquefy uniformly. And then we'll have a higher percentage of conversion to the 2212 in our instance. Do you have any questions?
Is the filament of the 212 is polycrystalline?
Yes.
So is this the reason it doesn't depend on the direction?
I think it's more along the lines that it's a round wire compared to a flat tape. So the round wire will have all kinds of random orientations, but in general they will be along the axis of the very, very thin filaments. So that's why they make them so small.
So do you know whether there is 2212 fumes?
Yes, 2212 flat tape is
that tape
readily
depending on the direction of the field?
Say again?
Did the tape depend on the critical current depend on the direction of the magnetic field?
I assume so, but I haven't seen that in writing personally. Anybody else?
I imagine you probably did, but when you were looking at the mass spectrometry of your stuff that you melted, did you also look at just the oxygen flow, without a sample to make sure that you don't have impurities in your oxygen?
Yeah, and that's why we
had to filter it there.
The filter,
okay.
right there,
Mm-hmm.
because we had
Water.
yeah we had
Looks like dry.
0.1% water, which I had a logarithmic reading on the mass spec, so it showed up very strong. As soon as we put that on, you can see any little spike. Another interesting thing is here, where it's swaged, where the filament is swaged in, in the very beginning, pretty much all my first 3 or 4 months there, we were trying to get this thing to work, and that was a gigantic mess. I eventually had to end up breaking this thing apart and replacing several parts. But there was a leak, but sometimes we could test it. No. First, we didn't know it was there, right? We just thought that our samples were giving off helium. Like, why is our sample giving off helium? Because I was doing this over several days, and then Hellstrom had me look at it, and it was giving data that was spiking and then coming down, and spiking and then coming down. And we looked at it over the time scale, it was a period of days. So in the morning, it would be very low, and then as they started to run experiments on the first floor of the ASC, it would start to go up. And then it would come down in the evening, because the helium that was coming out downstairs was going upstairs and getting into my little leak. And we never could close that off to helium itself, but we could close it off to O2, nitrogen,